Hello everyone, this is Mikel Garcia from Rokugun, and here today now we are going to explore the third part of the workshop that processes the GNSS data from the ACORN network for ionospheric monitoring. Remember that the ACORN network is the affordable receiver network that has been deployed in the context of the AMIC project. So here in this case, we are, if you recall, we just described in the past the network, this ACORN network, the way in which the data is pushed into the GNSS Science Support Center website and portal, then which are the receivers that we are using for that, and we just baked before how to get the data out of the network or of the portal. How can we assess the noise of GNSS receivers that are using the network? And finally, that we are going to do today, how can we use this data to compute a scintillation index, right? That's the use case that you can learn how to do it using this notebook. So the ROTI, the Rate of TEC index, is basically an index computed using the combination of phase measurements to detect if there is some scintillation event. The algorithm has been introduced in P et al. 2013, and it's actually straightforward. It's summarized in these 3 bullet points. So as inputs, we just need the carrier phase of GNSS measurements, at least at 2 bands. The output is going to be a time series of the rate of TEC index, expressed in tecus per minute. And the process is that for each and every GNSS satellite that is present in the data, we compute the ionospheric free combination of carrier phases, which we have done in the second part of the workshop. We compute the time difference of this combination. Then we convert that to the time difference of a slant TEC. It's simply the time difference of ionospheric free combination divided by a constant. And finally, we are going to compute the standard deviation of this time difference of a slant TEC across consecutive time intervals of 5 minutes. The results can be seen, for instance, in references like this one, whose figure has been extracted from Juan et al. 2017. Here we see different stations for different satellites. They are located at different latitudes, and then we can see these increasing values that can reach 15, 20, or even higher 60, no? for the case of the CHPI station for the PRN11. And this can be used as an index to detect if there has been scintillation. So a similar figure we want to obtain in this notebook. And to do that, let's get our hands dirty with this. So first step is, as usual, install the necessary packages that we are going to need for that. Then import some packets and data. Again, what we are doing here is load the sample data that we stored in the first part of this workshop. And then, since we have to use the LI combination, we need to define a satellite and 2 signals for that satellite. So if we are going to use GPS, so let's go with the 1C tracking channel and the public long code for the second frequency, the 2L. So we just fire the commands and then we compute the geometry free. Again, remember that what it does basically, it puts the 1C and the 2L data blocks in the same row so that we can quickly operate between them, because then the LI is directly phase A minus phase B, or range A minus range B. That's the LI expressed in meters, or the code combination, the code ionospheric free combination, also in meters. Okay, so now what we can do is plot, as we did before, the LI combination. So we have something like that, right? So decreasing trend, that's so far so good, nothing really different as we expected. So now let's go ahead and compute the time difference of slant TEC. To do that, the first step is compute the time difference of the ionospheric free combination. That's what we are going to do here, right? So compute the the difference using the NumPy library. This is a very convenient one. The problem here is that if we have n samples with a diff, we have n-1, and in order to make them consistent with the number of rows of the data frame, we just insert not a number at the very first sample. Then we do some quality check, right? So if we have some outliers, in that case outliers for us is that the ionospheric free combination is larger than, say, 1 meter. That mean the time difference is larger than 1 meter, we just ignore those samples. And then what we have to do here is compute this constant that divides the Li combination, right? In order to compute the time difference of the slant TEC. Remember that it's the geometry free combination divided by this constant. Once we have that, we can compute the rate of a slant TEC. Right, so we have some points here. Maybe if we put dots, it's going to be easier to see. Okay. Right, so we have basically a cloud of points. So now what we are going to do is divide this data series in chunks of 5 minutes and then compute for each of these chunks the standard deviation. That's going to be our ROTI. Right, so we basically do this. Right, so we first we had selected for one satellite. I just forgot to mention. Right, so we have, let's come back here. Remember that we selected the satellite data out of the LI, so the complete data frame. Right, so we are just operating for one satellite. Okay, and then for that satellite, what we are going to do is fire up this cell. This cell, what it does, right, it's takes the data of slant TEC for this specific satellite and then resamples the time series at chunks of 5 minutes. So the division of 5 minutes is done in this command, and then for each and every one of these chunks we compute the standard. That's what it's called functional programming, and it's very useful in that case. That's actually the convenience method provided by pandas, which are really handy in that case. So if we fire up these commands, oops, let me see, maybe I forgot to mention to fire someone. Okay, let's see how the fsat looks like. Okay, all right. Okay, let's look for the epoch. So epoch is there, so why don't it works? So let's see. Okay. So none of epochs are in the columns. Great. Let's probably regenerate the data at some point. Maybe I forget to fire up this one. Okay, good. Now it works. So probably I overwrote the satellite data somewhere. Okay, so now what we can see, we see that for each and every chunk of 5 minutes, right, we have a value. That's the standard deviation. For the following 5 minutes, another standard deviation. For the following 5 minutes, another standard deviation, and so on and so forth. Now what we can do is basically plot this time series, right, and get a similar picture that we obtained before. In that case, however, there is no scintillation event, unfortunately, so then we can see that we have a very nice and calm state of the ionosphere. If there would have been some ionospheric scintillation events, then we probably would have seen some peaks around here. So I leave it up to you to just explore the AMIC data and try to find some scintillation events, and obviously feel free to contact me if you find one and you want to share it. Okay, so with this we can conclude this third part of the tutorial on how to use these data labs for AMIC data processing for ionospheric monitoring. So I hope you enjoyed and you learned something out of this workshop, and if you have any doubt, please feel free to reach me. Thank you very much for your time.